my goal for today is sort of to hit the middle part. So I want to talk about applications and make sure we're very comfortable with that, because definitely we're going to see some applications. At least one for sure, because it tells us right there. So we want to make sure we're comfortable doing that. So there's a couple kinds of applications we might see. So let's talk about the things that we should be comfortable talking about. So the first thing is, you see here, growth decay. Now this is a very popular model, and in particular, this is really exponential. And so you talk about exponential growth, exponential decay. That's the type of thing that we talk about. Now, how do we know that we're in this model, or how do we know this is the right setting? Well, they might tell you there's some keywords. For example, they might say, aha, assume it follows the exponential type behavior. Okay, that's a pretty strong clue if they just tell it to you. The other thing that you might see is a phrase, something along the lines of the following, where it says the rate is proportional to something, the current amount. Something like that. If you see that kind of phrasing where it says the rate is proportional. Now when you think rate, what's that translate to in our language in differential equations? Derivative, yeah. And is the universal words for equals, proportional, some constant, and then proportional to the current amount is the idea. So like the population is proportional to how many people are already in the population, or how many bacteria or whatever it is you're modeling. Or radioactive decay, that's the case where K would be a negative value. The amount of algebraicum, make up some sort of chemical that, degrades over time. Well, it's proportional to how much there is currently. Now, why do we call it the exponential model? What is the solution to the exponential model? So if this is your differential equation, the solution looks like P of t is P naught e to the k times t. Yeah. So you should be familiar. If I see exponential model, I know automatically this is my differential equation. I know this is my function. And I'm ready to start filling stuff in. Now P0, what is this? Initial population. Great. That's usually given to you. K is usually not given to you. So what helps you solve for K? Okay, so I think someone said like doubling time. You might also see, if you're doing radioactive decay, words like half-life. Or more generally, just a second data point. So, I know the initial population is 100. After 3 years, it's 200. And so we can use that to say, okay, at t equals 3, I know my initial population and I know my population at time 3. Plug it in and solve for k. So pretty much these are very straightforward. No surprise, this was one of the first things we studied. Okay, so exponential growth, exponential decay. All right, I think we're comfortable with that. The next one, mixture problem. So mixing. Now, we didn't get to do one of these on the first exam. So what's this? Well, the picture, and I like drawing pictures here because it helps me understand. You have a tank full of some kind of liquid. Almost always we phrased it in terms of salt water. Doesn't have to be, but okay, so here's our tank, currently full. And there's something coming in, and there's also something going out. And then the question is, what can you say about some substance? How much is there? So these are the settings for mixing problems. When we talk about mixing problems, this is where we're at. All right, so now the question is, of course, what are we measuring? And it just depends on context. So almost always we talked about salt, so let's just say it's salt. It doesn't have to be. It's anything that we can throw into our system. And so we'll call that a quantity. It is an amount of salt. So when you go to set up your differential equation, you say, all right, there's Q prime. Well, how does the salt change? Well, how can the salt change? Yeah, you can either add, this is, things coming in, or things go out. So you figure out how much is coming in, figure out how much is going out, and the difference is what's the net change. That's how your quantity is changing. Did I lose my mic? Should I just talk louder? I for some reason it says this battery is dead on this device. Oh, hello? Hey there. Yeah, it still says it's dead. All right, well, maybe the next person. All right, karaoke night. Hello there. No, I probably should just talk louder. I think that'll work better. And if you don't hear me very well, just say, louder, louder, Steve. And I'll try my best. All right, so the way we look at this is we think about what's our change? How are things changing, in versus out? Now, usually when we talk about the in, that's a number. I know I'm writing this and you're like, ooh, hashtag, cool. But that's just a sort of a set amount. The out is the interesting part. Because the out depends on what? Well, it depends on how much there's currently in there. And so it's basically some multiple, and I'm going to be very, very vague, some multiple of Q is usually how this problem gets set up. Now, the multiple depends. You might say the amount of liquid, total liquid is fixed. It's neither being added or subtracted. That's great. Or it could be the case that maybe the brine level is going up. Okay, so then you have some function here. But at the end of the day, it's not so bad once you understand the basic idea. In, subtract, out. Okay, so given that that's the basic idea, let's just suppose we can do our setup. What does this problem become? What kind of problem is this? What techniques do we use? What? Linear, yes. Yes, this becomes linear. And away we go. So we can handle these. The main part is just getting the setup. Okay, and the setup, once you understand Q prime, in, subtract out, it's not so bad. Now, the other application I want to talk about, I'm going to skip logistic just because we've seen logistic. So in my mind, it's probably a lot less likely we need to worry about logistic. And so let's focus on things we need to worry about. The other thing, springs. So we want to talk about handling a spring mass system. All right, so what's our sort of setup? The basic idea is, okay, we have somewhere we anchor in. And we have our spring. There's our spring. We have our mass, our object here. What else should we throw in here? Yeah, if we're going to get the whole 9 yards, this is attached to some sort of a dampening device. And usually the way you can think of a dampening device working is like there's a sort of a plunger that's moving through fluid. And the key, the reason it dampens is if you try to push that plunger through the liquid, the faster you try to push, the more the resistance. And so the dampening is related to velocity. Now, the nice thing about the spring mass system is there's a nice big framework for it. If you understand the framework, you just have to fill in the boxes. what are our boxes? Well, there's 4 boxes. So you look like something x double prime plus something x prime plus something x equals something. And if you understand that that's what that's what the equation comes down to, and you know what goes into what box, then it's not hard to set it up. And once you have it set up, off to the races. Let's talk about the boxes. Box number 1. M. M for mass. Yes. So the mass goes into your first box. All right. Box number 2. C, okay, which is your damping constant. So your damping is related to velocity. And so that's attached to your x prime. All right, 2 down, 2 to go. What goes into our next box? Okay, wow, you guys, I should add these, since you're giving me these symbols. M, C, K. Someone called it spring constant, which is good. Now, where does spring constant come from? What is it often associated with? Hooke's law. So sometimes they give you K directly. Sometimes they'll say, the spring does something where if the spring has like a force of 10, it stretches a distance of 2. Then that's actually giving you information about Hooke's law, because Hooke's law says force is minus kx. So if they give you a force and a distance that the force stretches the spring, they're secretly giving you k. So that's what goes into there. All right. Now, the last box may or may not be filled, but let's just talk about what would go in the last box potentially. External forces, yes. So if there were something happening outside, maybe somebody turned on a special magnetic thing which influenced your object.
Would this also be like in what you've drawn? It's vertical, which means that gravity would be an external force?
Usually by the time we have gravity sort of has worked its way out of the system. And so don't worry about gravity. I'll say that again. Do not worry about gravity. All right. I'm on the record now. I say don't worry about gravity, and then if you go and watch the solutions to number 2, you'll see me worry about gravity. But that's because I can't say what I want to say because I'm on the record. So, anyways, all right. Once you have it set up, let's suppose there's no external forces. So you have, something x double prime, something x prime, something x equals 0. How do you solve that equation? Okay, meaning what? Yeah, you get m r squared plus cr plus k equals 0. And you find the roots. And off you go. Now, a couple things can happen. And there's some things that can happen which are interesting. If there's no damping, you actually look what you think springs look like. So it just keeps going up and down. So this is if C equals 0, no damping. Or undamped, I think is the official phrase. What are some other things that can happen? Wow, you guys are just going faster than I can even draw these. Okay, so one person was just going dump, bump, 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 bump. Okay, so there's undamped. There's this behavior where you oscillate, but it gets smaller and smaller over time. This is underdamped. And this is the case where you have complex eigenvalues, but you have a real negative part. So you have that e to the minus coming in, which basically kills it in the long run. There's overdamped, and that's when you've turned your damper up to 11. And what happens is you let your spring grow, and it basically says, I'm not going to be very springy, I just go back. So it's okay if you have a spring system and you're like, wait, I don't have sines and cosines. No problem, it's just overdamped. And of course, critically damped is very similar. It almost looks the same. Do you know the difference between the two in terms of, say, the roots of your polynomial? So critically damped is repeated roots. Overdamped is distinct roots. Now, one thing I just want to point out, there's a small check that you can do. And that is that the real parts of your roots should always be negative. So if you are doing a problem and you end up with a positive root, what does that mean? You did something wrong. You did not discover a new spring. You did not rewrite physics. So just make sure, if you're doing the test, you want to have these small checks along the way to say, oh wait, should this be positive? No, I don't think it should be. Let me correct my error, the error of my ways. All right. So anyways, these are, in my mind, the applications I want you to make sure you're comfortable with and you're ready for. And you should be able to do these. All right, any questions on applications?
Question.
Yes?
For a critically damped and overdamped, does that have an imaginary root at all?
There's nothing imaginary about this. Yeah. So overdamped is distinct real roots. Critically damped are distinct repeated roots, but they're real. So the imaginary part is the part that has you going up and down. Okay. So if you see something going up and down, then you have imaginary parts. But again, you don't have to have that. You may just really love damping your spring. So some people like to do that. All right, well, the next thing we should just make sure we touch on non-homogeneous. Because we want to make sure, hey, we can handle things like non-homogeneous equations. So let's do something very quick. Quick review. All right, so suppose you have, so I'll write down two equations. Y double prime plus y equals 0. Y double prime plus y equals 2x sine of x. One of these is homogeneous, and one of these is non-homogeneous. How do you know which is which? Yeah, the one that equals 0, this is the homogeneous. And unfortunately, this is a different homogeneous than the homogeneous we talked about in our last session. Non-homogeneous is when you have some interesting function here. And between the two, you really hope for homogeneous. Non-homogeneous, though, we should talk about how to handle it. What's our main technique for handling non-homogeneous? Well, variation parameters is sort of a universal technique, but it's not the one we like to do. Which one do we like to do? Undetermined coefficients. Yes. So make sure you can handle undetermined coefficients. So let's do a quick review of how we do that. So, all right. Now, it's actually pretty straightforward. And the name kind of gives away what we're going to do. We have some coefficients that are not yet determined. So we're going to figure them out. That's the idea of the process. And the way we begin is, well, if you have step 1, you gather the parts of your non-homogeneous side. So when I say the parts, I'm talking about, the individual functions. So for us, let's say I'm working off of here, that would be the x sine x. I don't worry about the 2. So now we have x sine of x. Okay, so that's the first thing. And now, the second thing is round out your list. And by that, I mean there's three things to check. First thing, if you have powers of x, then you need the lower powers as well. So, do we have anything with the power of x in our list? Yes. So what else needs to be on our list if we're rounding it out? Sine x. Because this x is what we have to go down. Not the x on the inside, the x on the outside. So we need sine of x. Then, the second point, sine and cosine come in pairs. They like to hang out together. So, if you see something with sine, you have to have a cosine pair. Do we need to modify anything on our list or add to our list? What do we need to add? X cosine of x and cosine x. The third thing, remove overlap with the homogeneous solution. And we do this by the bump. Okay. So that says we have to do the homogeneous part. Well, let's do that really quickly. Y double prime plus y equals 0. We turn that into that polynomial. R squared plus 1 equals 0. What are the roots? Plus minus I. So what are the functions? So remember, you might say, oh, it's e to the ix, e to the minus ix. But complex roots, we had this way of combining complex roots into real parts. So the pieces are cosine x and sine of x. So a cosine x, b sine x. So this is the homogeneous part. Is there overlap?
Yes.
So what do we need to do? Yeah, so we multiply until we get the overlap. Now, we only need to multiply things that overlap. So here, there's the cosine x, so you multiply by an x. And then you also have to multiply the x, cosine x by x, so that's x squared. Same thing with sine, x, and then the x squared sine x. So now, after you finish step 1 and step 2, and this is more than we would ever have you do on a test, but the process. The third step is put in your coefficients. So what does that mean? Well, going through we already used a and b, so we have cx squared sine of x, dx sine x, capital E x squared cosine of x, fx cosine x. And what's the last thing to do?
Plug and then find.
Yeah, plug into the ODE, solve for the coefficients. And when we talk about plugging it into the differential equation, we really mean you're plugging this whole expression into there. And that gives you a set of equations, system of equations, many unknowns. But we should be comfortable doing things like that. All right, so that's how we handle non-homogeneous. Any questions on that? You're comfortable? You're ready? You can do it? Good. All right, because we still have other topics to talk about. So, numbers 4 and 5. You'll notice that if you look at the sections, it says 5.2, 5.5, 5.6, which means we're skipping over chapter 4. Now, you can, because we had a conversation with the instructors earlier today, they said, look, it's okay if you use the techniques of chapter 4, but you don't have to. So you don't need to know the techniques of chapter 4. And if you look at them, you notice that there's some similarities. They both say solve a system with 2 ODEs. So the good news here is that this tells us we're in the 2x2 matrices. No 3x3s will be injured on this exam. So, good. That's great news for us. Now the thing is, we've got to do it twice. So we've got to be ready. We've got to be ready. Okay, so what's our basic setup? Well, our basic setup is we might have a system of equations. Let's say x prime equals 7x minus 2y, and y prime equals 8x minus y. Maybe that's our system here. And we want to talk about eigenvalues method, because it says use eigenvalue methods. But if we're going to use eigenvalue methods, what do we need? We need eigenvalues, and so that means we need a matrix. So know how to convert this into saying, oh, this is really the same as x. Now you can't tell that this is a bold x. I wrote it in a bold way. You're like, ooh, well, that's very bold of you, Steve. Yes. In other words, this x is really a vector, whereas this x is a function. All right. Equals something x. What goes into the matrix? 7, -2, 8, -1. In other words, the coefficients. Coefficients going. Now, that tells us we're now in our setting x prime equals ax. A is our matrix. Okay, so x prime equals ax. Now is the fun part. So, our basic idea is find the eigenvalues of A. Now, I say the basic idea because there's a couple of things that can happen. And once you have the eigenvalues, you always will be able to succeed in finding the eigenvalues. And we should also say the eigenvectors as well. But there's a couple of things that can happen. All right, so let's talk about 3 different scenarios you might encounter. And like I said, there are 2 problems. And there are 3 scenarios. So you better be able to handle all 3, because probably you'll see, I'm guessing you probably see at least 2 of them. So the easiest scenario, in some sense, is if you have distinct real roots. Okay, so you have a matrix, and you have, I have distinct, when I say distinct real roots, I should say the roots are the eigenvalues. So the roots are the characteristic polynomial. Okay, so distinct real eigenvalues. All right, so the procedure for that one. That one is pretty straightforward. So what you'll do is you have your eigenvalues, your eigenvectors. So you have your first eigenvalue, your second eigenvalue. Then you'll have an eigenvector for your first eigenvalue, an eigenvector for your second eigenvalue. You'll succeed in finding these things. And then you say, okay, our solutions have the following form. So if you think back to, we talked about the characteristic polynomial when you had those differential equations before. It's the same philosophy, where we had e to the root times t. So it's e to the eigenvalue t, then times the eigenvector. So times it by v1. That's one solution. And e to the other eigenvalue t times your other eigenvector v2. Throw in some constants, and there's your general solution. Okay, so that's how you handle distinct real roots. No big surprises. Very straightforward. Which means there's some interesting things which can happen. All right, what else can happen other than distinct real roots? Repeated roots and imaginary roots were the 2 things. So let's start with repeated roots. Ah, yes. Repeated roots. Good times. Good times. Okay, so this one is slightly different. So you have to make sure you know what is going to happen. So when we talk about repeated roots, that says we have lambda twice. So lambda, lambda. Those are our two eigenvalues. So the process is, you find the following. You take a minus lambda I times v equals 0. 0 here being the 0 vector. What does v correspond to? Yeah, v is what you call the eigenvector. And then you're like, aha! What we'll do is we're going to work our way up. And then we'll introduce some new vector. We'll call it double v. See, because there's like two v's there. And we want a minus lambda I times double v equals v. Now v has v is your eigenvector. W is what the book called the generalized eigenvector. But this is important because this helps you do the bump. So you have to have it handy. You have to go through the process. Make sure it's a minus lambda I, not lambda I minus a. It makes a small difference. Small enough difference so that you'll lose a point. We don't want to lose any points. Each point is precious. Okay, so that's the vectors. What do the solutions look like? Well, the first solution is the same sort of idea that we had before. We'll have e to the lambda t times an eigenvector, and that eigenvector is v. So that's solution number one. What's the second solution look like? Okay, e to the lambda t. T times which vector? Times your vector v plus double v. Yep. Throw in some constants, and we have our general answer. All right, so that's our repeated roots. So know how to bump up as needed. All right. That leaves us with another possibility, which we already mentioned. Any questions on repeated roots? You got it? Yeah, the good news is it's 2 by 2, so you never have to go past this point. And you might say, do we always have to do that for repeated roots? And the answer is, well, if it's 2 by 2 and you have repeated roots, unless it's the most boring system of differential equations you can imagine, yes, you have to do this. And you might say, what's the most boring system of differential equations? Things like x prime equals 5x, y prime equals 5y. Yeah, that's pretty boring. There's no interaction. So, all right. Complex roots. It gets its own page. Well, it is complex. All right, so what do we do? All right, so here's the basic idea. So the nice thing about your eigenvalues is that they come in pairs. So your eigenvalues will look like a plus or minus I times b. And your eigenvectors will turn out, they also come in pairs. So a plus or minus I times b. We have to be a little bit careful here because there's a little bit of ambiguity. And you might say, okay, but how do we get to the best scenario? So let's have a reference here. So let's suppose we have A is this matrix 3, 2, negative 5, and 1. And I'll tell you, I already computed the eigenvalues for this before I came to class. 2 plus or minus 3 times I. It's not hard to compute these eigenvalues, but that's what they turn out to be. Okay, so now I regret using A. Well, that's okay. I regret many things. All right. Now, the key here to go forward, I really want to emphasize this with an example. So let's just focus on the 2 plus 3i. And I want to grab the eigenvector. So the key is to look at a minus lambda I times v equals 0. So just be careful here. So take a minus lambda I. What would be the first entry? Okay, 1 minus 3i. Here, the next entry? 2. Okay, now we're into the lower left. Negative 5. Okay, the bottom right. Negative 1 minus 3i. Okay, and we're multiplying by some vector v. I'll call it v1, v2. We want to get 0, 0. Now, you know, this is a nice thing. You know, because it's an eigenvalue, and there's going to be redundancy. And what that really says is, instead of trying to do any kind of elimination, if you just want to save yourself time, and who doesn't want to save time on a test? Say, look, there's 2 equations here. There's the first equation. I'll write them both down just for reference. And the second equation. The point here is one is a multiple of the other. Which one do you keep? Haha, trick question. You keep whatever one you want. Ha! It's which one do you want to keep? Well, okay, someone said the top. All right, great. Cross out the bottom one. And you just have to find any v1, v2 pair that works. So don't be creative. This is not a time for creativity. So how do you not be creative? Well, you basically say, look, these coefficients will clue me in how to choose my v1, v2. So what's the v1, v2 that works? Do you see something?
V1 is 2.
Okay, if you choose v1 to be 2, all right, and then what would v2 need to be?
1 minus 3i.
Ooh, be careful there. Those would double up. So if you do the negation. So if it helps, you can move this 2v2 to the other side so that you have an opposite sign. So just make sure you don't want them to add together. You want them to cancel. So you want to flip the sign on one of them. Okay, so what's the point here? So for this eigenvalue, your eigenvector can be split into a real part plus I times what we call the imaginary part. All right. Great. Now, but how does this help us with our solutions? We're not going to find the second eigenvector. It's actually freebie. So if I want 2 minus 3i, I just flip the plus to a minus. And that gives me my second one. But here's the key. You take e to the at cosine bt plus I e to the at sine bt. This part is e to the lambda t. And then you multiply it by your a plus I times b. And this part is your v. So it's the same basic setup, e to the eigenvalue t times eigenvector. The same thing we've been talking about with our other situations. But now, here's the fun thing. What do you do? So for our specific case, if we just now apply it to here, so you'd have e to the 2t cosine 3t plus I e to the 2t sine of 3t times 2 minus 1 plus I 0, 3. What do you do? How do you finish it up? Because that's, how do we make 2 solutions out of this? What do you mean by break them apart? There's a nice 4-letter word. Foil. Yeah, foil and group. So what do I mean by foil? Well, you really are going to end up with 4 terms when you expand it. 2 terms will have I. two terms won't. So that's how you do the group. So specifically, if you come up here, the terms which are the real parts, take the real part times the real part, the imaginary part times the imaginary part, and you put those together, and that's, solution number 1. And on the other hand, if you do your real part times your imaginary part, and your imaginary part times the real part, put those together, that's solution number 2. So for us, we would have, so e to the 2t cosine 3t times 2 minus 1. I squared, don't forget you need to take care of that. I squared would be minus e to the 2t sine 3t, 0, 3. Okay. That's solution number 1. We'll throw a constant in front, plus some other constant. Now the imaginary parts, e2t cosine 3t, 0, 3, plus e to the 2t sine 3t, 2 minus 1. Now some people are young and really good at memorizing stuff, so they actually sort of memorize the final answer. I'm not able to store that much in my mind anymore. So I just like to remember the process, FOIL and group. That helps me find my solutions. Okay, so that's it, right? We know how to handle distinct roots, repeated roots, complex roots. That's the only situations we can encounter. So.
Could you do like a 5-second run through finding eigenvalues?
Finding eigenvalues, 5 seconds. All right. 5 seconds on the clock. No. So to find the eigenvalues, the key here is it comes from finding roots of a polynomial. And you look at the determinant of, well, I did it lambda I minus a, but probably it's better to go with a minus lambda I just because it's more consistent that you see it this way. So take this 2 by 2 determinant, set that equal to 0. What you really have is a minus lambda I is a quadratic equation in terms of lambda. And you solve for that, and that gives you what you need. I hope. So that's the process. All right, we have a few minutes left, and there's something else we need to talk about. And that is the fundamental matrix. So make sure you know how to do it. It's very clear, 100%, there's going to be some question. Because look at it. There's just one section attached to that problem. So you know that it's coming. And since you know that it's coming, you're responsible for being able to answer that question. All right, so let's talk about it for a few moments. Okay, so we have our fundamental matrix. And, it has the word fun, so it can't be that bad. Anything that's fun has to be good. So the idea is you have phi of t. What goes into your fundamental matrix? Your solutions. Yes. These need to be distinct solutions. And distinct is just a stand-in for the fancy word linearly independent. Okay, so you have distinct solutions. And so when we talk about distinct solutions to our x prime equals ax. Now, fundamental matrices are not unique because the solutions can be expressed in different ways. You can scale a solution by, say, a factor of 2. It's still a solution. So there's one really, really special fundamental matrix, and that is phi of t times phi 0 inverse. This is unique. There's only one of these. Once you multiply by phi 0 inverse, it makes exactly one matrix. This matrix has another name. What do we call it? Yeah, e to the at. So if a problem says compute e to the at, it's like, oh, find phi of t, multiply phi 0 inverse, and we're good. Let's just remind ourselves very quickly. A, B, C, D inverse. Do you remember what that is? 1 over AD minus BC or minus CB, right? This is also called the determinant. And then swap the diagonals and change the sign. Now, if you're not sure if this is right, what do you do? And how do you check? Yeah, multiply with the matrix you were starting with. And if you don't get the identity, don't just shrug it off, say, no, redo it. Redo it until you get what works. Now, why do we like e to the at? Well, if x prime equals ax, and we have x of 0, so in other words, we have our initial conditions, then what's true? What is x? Yeah, e to the at times x of 0. So if you see a problem that says use e to the at to solve an initial condition, then you can say, aha, once I have e to the at and I do a lot of work, then the rest of it's super quick. Just almost pops out. Now, 2 more things I want to talk about. I have a minute. I can probably squeeze it in. A couple of checks for your e to the at. All right. If you take t equals 0 and plug it in, what should you have? Think of e to the at, plug in t equals 0. That looks like e to the 0. Intuitively, that says 1. In terms of matrices, that says the identity matrix. So if you plug in t equals 0, you should get 1, 0, 0, 1. If you don't, mistakes were made. If you take the derivative of this matrix and plug in t equals 0, what do you get? Just think intuitively what should be true. If you take the derivative of e to the at, what should that look like? Use your intuition. A e to the at, plug in 0, we should be left with a. So you can run these 2 tests really quickly and just say, hey, is this right? And if it's not, what does that mean? It means check your work. Go back. Now, I know officially time is over, but do you want to know one really cool way to compute e to the at? Sure. Now, this only works in one of the 3 special cases we were talking about. As a reminder, those 3 special cases were distinct roots, repeated roots, and complex roots. Which one has the shortcut? Okay, it's not distinct. It's not complex. Yes, good. You cracked my code. Okay, so here's the cool fact. The reason that this works is because if there's this alternative way to compute e to the at, where you have like that big infinite sum. 99% of the time, that's a terrible way to compute it. But if the roots are repeated, what you can do is rig it so that all the terms disappear except for just a little bit at the start. So if a is 2 by 2, and the eigenvalues are lambda, lambda, so it has to be repeated eigenvalues, then e to the at is equal to e to the lambda t times the identity matrix plus t times a minus lambda I. That's it. I know, I'm sorry. I should have had more jazz hands. Whoa! So that's the shortcut if you know it. You don't have to know it. You can always do it. Find the fundamental matrix. All right. Have a good day.